Can everyone hear me okay?
Hey, Carson. Yep.
Hey,
Nice to see you.
yeah, good afternoon.
Hey Carson, how are you?
I'm doing well. How are you?
Good, good.
Good. You have a really nice background.
Yeah, thanks.
And I think Chris and Carson, you two just recently won a silver medal for the Kegel competition. You worked together, right?
Yeah, that's correct.
Yep, yep.
Yeah, that's really, awesome.
Yeah, we're pretty lucky.
Yeah,
That
I
was a
know
fun
you're,
experience.
yeah, you're competing with like people from internationally, and it's pretty hard to have those really top ranks. So maybe in the future we can have some boot camps to, have people to work on some Kegel competitions together.
Sure, sounds good.
Yeah, absolutely.
Okay, great. I think I'm just gonna start today's intro. Will people are still joining us? So for today, we're in our week 4 of our Python bootcamp, which is the last week. I think we all need a really big kudos to ourselves that we have, still keep learning until the last week of the Christmas holiday. So really proud of our course leaders and also proud of all you guys. So for today, we have our course coordinator Jing will moderate our session. And for today's course content, I changed a little bit background to match the holiday, the festive environment. So
Nice.
for thank you. So for today's class, we will learn kind of an introduction to machine learning. And for the first part will be supervised learning that is taught by Daniel Ma, who is a data scientist from Statistics Canada. And he's also in, I think he's really close to finish his PhD from University of Calgary. And he's really experienced in data science and machine learning. So today he will do uh, intro for the machine learning and machine learning roadmap, machine learning model structure, support vector machine and kernel trees. And after that, we have a break and 2:30 for 10 minutes. And Jim will distribute our participant attendance sheet so that if you have any questions about our records of your participants, that you can just send us our messages before the end of this class. And after that, Chris will give us an intro about the unsupervised learning. And Chris Chen is a really well-known data scientist in the Alberta developers community. He's a senior data scientist in Imperial Oil, and he has been teaching in our previous a few boot camps, and I'm sure a few of the participants in our Python bootcamp have in his class before. So for today, Chris will give us some introduction about PCA, which is Principal Component Analysis, and the clustering. Without further ado, I'm gonna pass the torch to Daniel, and I hope Daniel and Chris can have more formal and proper introduction of themselves before the course. So it is all over to you, Daniel.
All right. Let me share my screen right here. All right. Thanks, Jingli. So I'm going to take over today's lecture right now. This is the last week of the bootcamp, right? I think so. Week
Yep.
4. So just a little bit introduction on myself. So I'm a guy that's super obsessed with machine learning. I've been doing machine learning related projects for over about like 6 years or 7 years right here. Just like, just Yingli just mentioned, I'm like as the last stage, probably gonna graduate very soon with my PhD. kind of like a research area was actually on the combination of economics and also machine learning. So basically use machine learning to solve all different kind of like economic problems over there. I'll give you more details later, probably in the next several pages over there. And also, I am also the head instructor of the machine learning bootcamp. So you probably already know me from the previous bootcamp already. So that's everything about me. So if you want to have a connection with me, just feel free to click this link right here. Just find me on LinkedIn. We can actually start a conversation from there. So today, me and Chris, we are going to do a little bit like a really kind of like vanilla or naive introduction to machine learning. I'm going to do the supervised machine learning part, and he's going to do the unsupervised machine learning part. So since we only have 3 hours, we are not going to cover everything. Excuse me. That's actually not impossible. So each of us actually come up with a great idea. That is, we are going to go through one of the most popular models in each kind of area. For example, I'm going to go through SVM, and he's going to go through PCA or K-means, or I think it's PCA over there, like according to what he shows over there. So we try to use this simple example to demonstrate how supervised machine learning and unsupervised machine learning works. So before we actually started into the supervised machine learning, I just want to give you guys a little bit kind of outline, or kind of like the general content we're going to cover today. So the first part, we are going to go through the basic definitions of machine learning. Basically, try to answer the question like what machine learning is, why do we actually study machine learning, and how we actually started machine learning, like a roadmap to machine learning. And after we finish that part, I'm going to tell you a little bit of story on the supervised machine learning, exemplified by a supporter vector machine, which is the SVM right here. So it has 2 parts. First of all, I'm going to actually go through the theoretical framework. And after that, I want to show you, a concrete example, like how to actually use a package from sklearn to do classification using SVM. Okay, first part. So what is machine learning? Machine learning is not fancy. It's actually defined as just using algorithms or computational statistics to learn from the data without being explicitly programmed. So basically, it is based on the previous models, a lot of models we already know before. So supportive vector machine, random forest decision tree, those kind of models have been invented years, maybe 20, 30 years ago. But they never actually been programmed and actually made into the package, which is really convenient to use until today. So machine learning actually achieves that by actually using a lot of algorithms and also computational statistics to make it more convenient over there. And it's actually a subsection of artificial intelligence. If we actually try to attribute that to the computer science field, right there. So machine learning is actually everywhere. So basically, everything you have today on your computer, it can be related to machine learning. For example, Google search. When you actually search a word, for example, if you search good, G-O-O-D, it might have another word come out. So how does the searching engine actually know that word is going to be the word you're searching for? Right? So basically, you just memorize your historical search records, or based on the frequency of other people's search, and just recommend a word to you. So behind that is actually machine learning. And also the YouTube video recommendation, Amazon product recommendation, image recognition, self-driving system, everything are actually based on machine learning. So if you want to have actually have a better idea of what machine learning is, you're welcome to actually click this kind of like a link right here. Yufeng Guo, who is actually the developer and machine learning advocate at Google Cloud. He's an expert. He has years experience in machine learning, and he actually, I think his definition of machine learning is very, very detailed and concrete and very easy to interpret. So that is the definition of machine learning. But why do we actually study machine learning? Why is that so important? So, I mean, think about a lot of problems you try to solve every day, like the daily problem you try to solve. For example, one of the problems I have when I was doing my first internship at Loyalty One, which is the Air Mile program or the Air Mile card. I think all of you guys have that. That is try to actually do the customer's segmentation. So basically, we have the records. We have all the transaction record from each of the consumer, like from Chris, from Jing, from Xinli, everyone. But we try to figure out what kind of consumer you are. Like, are you a junk food eater? Are you health eater? Are you a luxury consumer? Or we try to actually categorize everything or every consumer into different kind of groups over there. But we don't have the labels. We can only rely on the transaction data to actually do that. So basically what I did back then is try to use the LDA model, which is called the latent dirichlet allocation model. If you are interested, we probably can talk a little bit more after this. So that model is actually unsupervised machine learning model. What it takes is just a bunch of like the products you purchased as a person, transform that into a list of the words and use those kind of words. And based on the prior possibility, we actually assigned it to the LD model. It can actually give me different kind of categories or different type of consumers. For example, we have a bunch of different kind of baskets right here. After the transformation from the LD model, I know whether you are a Popeye, you like Spanish, or you're a balanced diet, kind of eater, or you're just a junk food eater. So basically, one snapshot of the result looks like this. So on the left-hand side, we have 6 different group of consumers. And every time when you click one of the group right here, you can see what kind of like a products.
I just want to FYI that you're not sharing your notebook in the screen. It probably.
Oh.
We have.
You guys cannot see my. Oh, okay, sure.
Right now you are sharing your desktop, but just the calendar.
Can you guys see that right now?
Yep, we are back on the track.
Okay, sure. Sorry about that. So basically, like I mentioned previously, what I do is actually use a bunch of like a basket records and put it into the LDA model. It can tell me what kind of group consumers you are. So a snapshot of that is just like this. On the left-hand side, I have 6 group of consumers right here. So every time when I click one of the group, I can see what kind of like top products or the most frequent purchase products you have. And based on those kind of products, for example, if I click this group 1 here, it has mushroom white right here, onions, celeries, red bell sweet peppers, but no meat. But meat is actually at the bottom. But most of the stuff on the top is actually the vegetables. So in that case, we usually just kind of conclude with this kind of group of consumers as a vegetarian group over there. So if I know who you are, and then I go back to the data set, I find your kind of like car number. If I know who you are, then the next time when I design the offers, I will actually recommend more kind of vegetables instead of like meat to those kind of people over there. So I only finished the initial stage of this kind of project. Then I just leave it to other colleagues over there after my intern. I think they have been used this for the offer production for I think since last year over there. So yeah, that's just one example how why machine learning is important, because it actually helps us to do a lot of different things. Like especially in the industry, efficiency is the ultimate goal. A lot of like companies over there try to look for the business solution to improve the efficiency of their daily working. So machine learning actually can accelerate that, using through different kind of tools, just like the LDA model right here. Okay. So next part is this machine learning roadmap over there. So the roadmap can be complicated, but I think I oversimplify the roadmap a little bit right here. So I'll start from the like a general structure of machine learning right here. So the machine learning actually has 2 parts. One part is supervised machine learning. Another part is unsupervised machine learning right here. Okay. So for supervised machine learning, that is an algorithm that takes labeled data and creates a model that actually can make predictions given the new data. So the most important kind of like feature of the supervised machine learning is that all the data are labeled. So basically, you do not only have X, but you also have the Y. Okay, so that's one of the most important feature of the supervised machine learning over there. So under supervised machine learning, there are two different kind of like tracks. One is regression, one is classification. Basically, essentially, they're the same, but they target at different kind of like, type of data over there. So, so for example, regression actually, actually takes the data usually which has continuous outcome variables. So basically, the label for each kind of data point is 90% of the time, most of the time is actually continuous. For example, if you try to predict, the future price of the stock based on the past price movements, so that could belong to the regression category over there. So the classification is actually a different kind of like algorithm, which actually use the categorical outcome variables. So basically, for example, you might have, kind of like data with the photos of animals, each labeled with its corresponding name. So if I see, for example, if I just want to do a classification of this picture, so each of this kind of like a fruit right here is gonna label it as orange, 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 apple, orange, orange. So it's not continuous, it's categorical. So in that case, we usually call the supervised machine learning algorithm classification. Okay, so for the unsupervised machine learning, that could be many different cases as well. But to summarize a little bit, unsupervised machine learning is when we do the data that has not been labeled. So basically, all the data has no label. You only have the X, you only have the features or the variable to use it for the prediction or for the classification, but it doesn't have a label or doesn't have a category. So the goal is to actually try to find a pattern and create a structure in the data in order to actually, find its like inferred label or categories over there. So there are two types of unsupervised machine learning right here. One is clustering. So clustering is just like grouping alike data. So clustering in supervised machine learning is classification, except it doesn't have the categorical label right here. Okay, so basically, it's actually try to put all the like data point that has a similar properties or feature into one group. However, when we actually compare to the data to another group, they should be very different. So I think there's one example right here. Yes. Can you guys see the screen right here? All good. Let me double check for you. Yes, okay. So this is one of, I would say, fancy, probably. This is very fancy. I'll just close this. This is one of the very fancy, product made by Hubble, which is one very expert like machine learning engineer on GitLab. So basically, what he does is actually try to put all different words into embedding, and then just structure all the embeddings into like universe. So basically, every single point here is one center word. It can be linked to other different kind of word over there. So let's turn right and turn up a little bit. So for example, if I click that word, Firefox, and the next word related to that, let's just look into that part a little bit, is Internet Explorer. And another word is Firefox, Mozilla Firefox, IE, right? So all the similar words are kind of linked to this kind of word right here. Okay, so each word has each word comes with a text. So basically, we know how to pronounce a word, we know how to spell the words, but how do we actually group the words into one group? Like, how do I actually group Chrome and also Firefox into one group? Because they all are international, like Internet Explorer, right? How do I do that? So this is actually unsupervised machine learning. We don't know which group it belongs to. I don't know what Firefox belongs to. I don't know what Google Chrome belongs to, but I can find a way through the word embedding to actually structure them into one group. So similar examples can be Linux right here, right, which is a program language, and then Windows Vista, Linux, capital Linux, and like small letter Linux, Unix, right? So all those kind of words have the similar kind of properties over there, like Windows over there, right? So you're very welcome to explore this kind of word embedding universe yourself. If you search any word over there, you will find the cloud that basically belongs to specifically belong to that word over there. So this is a really fun experiment. I can actually use it to show the clustering. So this is actually one example of clustering. Okay. So another kind of example is called dimensionality reduction, or another thread. So dimensionality reduction is actually trying to compressing the data by removing irrelevant or unimportant variables and holding onto principal ones without actually losing the structure or the meaningful or the general kind of structure of the data set. So for example, if you look at this group right here, is this kind of picture right here. Suppose we have 3 dimensions right here. That basically means we have 3 variables, X, Y, and Z. And we have so many different data sets over there. But we have 3 dimensions and 1,000 positions or 1,000 data points over there. But it's really hard to actually do the classifying or the clustering, trying to actually group one to find one group which is totally different from another group. So what we can do is let's just compress it from 3 dimensions to 2 dimensions right here. It looks like this. Okay, which makes the problem a little bit easier. Then we can do a little bit more, compress a little bit more by compress that from 2 dimensions into 1 dimension, like this. So now we can do a classification in the middle over there. Okay, so dimensionality reduction essentially is one type of clustering, but it has different goal. So the goal is actually try to reduce the dimension of the features you have and actually keep the general structure on the meaningfulness of the original data set. So for example, if you try to do, I don't know, the oil price prediction, suppose you have 100 features. You have the past price, you have the location of the oil field, you have the salaries of the oil workers, and you have a lot of different kind of features over there. How do you actually select which ones are important to do the clustering or to do the classification? Then you can use dimensionality reduction. It helps you to do that. Okay. So machine learning also have great overlap with other advanced AI topics such as reinforcement learning, deep learning, natural language processing, so on and so forth. So reinforcement learning actually uses a reward system like AlphaGo. So basically it learns from the try and error steps it make every single time. So deep learning actually utilize or adopt the neural networks, which is more like a human brain, which is more complicated than machine learning to do a classification. And usually it works way more better than just like a machine learning because it has complicated neural network structures and also lots of hyperparameters to train over there. Okay. But we are not going to go to that far because those are just super advanced topics over there. But maybe in the future, we can open several courses actually focus on this. But for now, I'm just going to give you guys a simple kind of example of the machine learning, which is one or the supervised machine learning right here. Okay. So the last part of the general machine learning is the structure of the machine learning. So basically, this kind of a section tells you how we actually train a model, how we employ the model, and how do we actually put the model into production, the whole workflow. So starting from data collection, right, or data cleaning, data preparation. In order to use a machine learning model, you have to have the data. So basically, that's the first step. Second step is called explanatory data analysis, or EDA. This is a common word used a million times in machine learning, lots of interviews. We don't actually spell the full name. Most of the time, we just call this EDA. So this process is actually visualizing, cleaning, and also analyzing the data to extract insights from that. So basically, for example, The goal is to actually maximize the insight into a data set or undercover underlying structure, extract important variables, detect outliers, and so on and so forth. So basically just the initial preliminary step to actually look into the data and see the structure and try to find a general feeling or general kind of like thoughts on how the data look like. What can we do with the data over here? Okay. So the next step would be feature engineering. So feature engineering is actually the process of transforming the raw data into features that can be better used for prediction classification. So for example, if we try to predict the weight of different kind of like genders, so we can just use a gender as a structure, but also we can just use years of schooling as structure, right? But what if we just want to use both? We can just use the interaction of the both. We can just use gender multiply years of schooling and to represent, you know, the year schooling for each gender over there for as a new feature for the, you know, kind of like a wage or salary prediction. So the next part is model building. So this part basically is model selection or model comparison over there. So you have different models and what's the pro and cons of each model, and which one should you choose after a lot of comparisons over there. After you select a model, we are ready to train the model. We can just you know, put the data into the model, start training the model, and after using different kind of techniques like cross-validation or regularization, and after that, we can just do the evaluation on the model, like the performance. Like for example, if we try to do the prediction, then we care about the accuracy of the prediction, how accurate, you know, the prediction is compared with the real data or the real label over there. So after that, we're gonna do like tuning or parameter tuning or model optimization. So we select a model and we know this model is gonna be the model we use, but how actually can we improve the specification or model setting to make it optimal model? That is, we need to find the hyperparameters that actually can be used to improve the accuracy or the performance of the model. I'll give you more details on the hyperparameters later when we talk about SVM over there. And after that, so basically we finish, you know, all the behind screen steps, we are ready to make the model into production. Okay. So everything so far sounds a little bit abstract. So now let's make it more concrete or more kind of like detail. So let's think about one really popular supervised machine learning model, which is called supporter vector machine, SVM. Okay, to start, let's consider a binary classification problem on two classes. So suppose we have two classes right here, red and yellow. Can we do the classification just using single lines? My question for you guys, can we just do the classification using single lines? Or alternatively, we can just use a simple classification. Can we do that? Can we just use the lines to do the classification right here? Yes, we can, for sure, because, you know, it's easy, right? There's a gap over here. You can do the classification using lines. But we can, but we better not to. Why? Since we can, there's a gap right here. I can fit a line right here, but why just use a single line? Why not? Let's move to the next picture. If you try to do a classification using a single line, how many lines do you have for this group, for this kind of problem? 1, 2, 3. That's just a 3 I can come up with, but you can come infinite numbers of lines right here. Okay, now the problem is, if you have infinite classification threshold or decision boundaries or lines right here, suppose we have a data point X right here. Is it a red class or is it a yellow class? We don't know, because we have so many different kind of classification. For example, using this one, that's yellow. Using that one, that's red. Using this one, red, right? But which one it is? We don't know. So that's why we don't use a linear classification in this case. It doesn't satisfy our needs to make precise prediction. It only make predictions that seems, you know, kind of like right, but actually we don't know whether it's right or not. Okay. So there are three different, separators which never actually perfectly discriminate between these samples, just like I mentioned over here. Depending on which one you choose, a new data point like an X right here, it might be assigned with a different label, right? So that's why we are going to use a supporter vector machine. So supporter vector machine can solve this kind of problem because it's a discriminative classifier formally defined by separating hyperplane. So we are not using a line, we're using a hyperplane here to separate those. Basically, we are trying to find the gap, the widest gap to separate the two groups. Okay, so in other words, given labeled training data, the algorithm outputs optimal hyperplane, which categorizes new samples. So, excuse me, in two-dimensional space, this hyperplane is just a line dividing a plane into two parts where each class it lays either side. So that's looking to this, the same kind of, we are still looking at the same kind of problem. But if we try to use SVM or supported vector machine, what it gives us is this. Okay, it doesn't give us a single line, just like in the middle. It gives us a hyperplane over here. So that widest margin over here. Okay, so if any points actually, are left in here, right here, then it's red. Any point in the middle is unclassified. Any points right here is yellow. Okay, so it's a hyperplane, it's not like a line anymore. So this is actually a dividing line that maximizes the margin between the two sets of the points. Notice that a few of the training points just touch a margin, like this one, that one, and this ones. So those are called supporter vectors. Those are called supporter vectors. Okay, so it is the supporter vectors that actually define a hyperplane over here. These points are the previous like elements of this fit. Those are known as supporter vectors, and those are also why the algorithm is named as supporter vector machine right here. Okay, so I think this is very clear. From this, you consider this like an advantage of SVM compared with the linear discrimination or over there. Okay, so the next kind of part is more like a mathematical part. I mean, you try best to understand this, try best to interpret this, but if you can, that's okay. But this is very commonly asked questions, or a lot of like interview related, kind of questions will be in this kind of field, according to my personal experience over there. So SVM has very interesting loss function. Since it's a model, it must have a loss functions to actually help us to minimize the loss, to make the prediction more precise. So consider a binary classification problem with only two classes, with label 1 and label -1. Okay, positive class and negative class over here, respectively. Then the soft margin, or the generally, most of the time we just use a soft margin loss function for SVM. Theoretically, there are hard margins and soft margin SVM, but later the latter is more popular and commonly used these days. Because the previous one, the hard margin has zero tolerance for misclassification. So if you want to know more about soft margin and hard margin difference, you are welcome to click that button or that link over here. It will give you more, concrete introduction over there. So the loss function for SVM is we're going to minimize the weights of each kind of like features over here, but we are going to minimize 1/2 the weights, the square summation of this kind of weights over here. And plus we're going to have a constraint over there. So the constraint is this part. That is the sign of your label, the sign of the output variable, the sign of y, and the sign of the predicted label, or the sign, yes, this is the predicted label, must be greater or equal to 1 minus epsilon I right here, where epsilon is just an infinite smaller value right here. So basically it's that the sign of the output variable and the sign of your predicted variable must be same. So if you predict y is 1, then this one must be 1 here. Otherwise, if your prediction is different than the real kind of label, you're gonna face a penalty right here. You're gonna face a penalty right here. Okay. So I mean, think about it. If this actually constraint is valid here, if it's satisfied, then constraint will be satisfied and no contribution is actually made to your loss. If that's the case, then this part will vanish because we don't have any contribution to the loss right here. But if that's not the case, then constraint term, this part will not be satisfied and a contribution is actually made to the loss. Alternatively, the point that actually doesn't satisfy those kind of constraint will be penalized. So for example, the points in the middle. Okay, the points in the middle will be penalized right here. And smaller c here, another kind of feature is like smaller c here makes the cost of the misclassification low here. So basically, if we have a smaller c here, this term will be smaller. And our goal is to minimize the summation of the two terms right here. Then the cost minimization will be small. Then this is not allowing more kind of like some to wider kind of cushion or allowing more kind of flexibility on the misclassification over there. But if we have a large c, basically that means we impose a really strong constraint on this kind of like regularization parameter on the constraint right here, then it would actually make that into a really hard margin or close to a hard margin, make the cost of misclassification very high. So it's forcing the algorithm to explain the input data stricter and potentially it could overfit over there. Okay, so what do I mean by that? Let's just look at several examples right here. For example, if we just look at this kind of like classification algorithm over there, if C is huge, that basically means any point actually falls into this kind of margin will be penalized, very hard. So basically, any points inside the margin will be actually the points that actually contributes a lot to the loss function. Okay, but if this is like a soft margin, if actually it doesn't have a huge C over there, then any points actually inside here wouldn't actually be penalized that hard. So try to understand in that way. That's like the most intuitive way I can try to explain right here. Okay. I guess I will just pause here for a second, try to answer some questions.
Yeah, I think we have one question about the SVM you just talked about, but I'm not quite sure about this question. So it's from Sully. He asks, what if we have more data points? Will it change the hypothesis? I'm not sure what the hypothesis mean in the SVM.
I suppose a hypothesis is try to find the maximum margin, or hyperplane to separate different kind of groups over there. So basically, if that's a hypothesis, it wouldn't change. If you have more data sets, if you have 3-dimension data sets, 4-dimension, 5, 6, or 7, even more dimension, the goal is still the same. But it's not like just like this, that simple. It will be like, a hyperplane that actually separates, the upper points and lower points, or left points or right points. You would have different kind of hyperplanes over there, which intersect with each other and try to separate those different kind of points over there.
I see. Thank you. Another question is about the visualization of the network map. It's from Wayne Johnston. So what program or libraries or what API did you use to make the
good question.
Network?
So it's a combination of different kind of programs. So basically the foundation is Python. And for that one, we use Word2Vec. I can just type right here. That's one of the natural language processing model we use, one of the most basic one. Node. Word2Vec. It's one of the neural network model actually. You commonly using that natural language processing area, which actually rely on the text word, context word, and also the center word. Try to group a different word into one group over there. And after that, you can just use, I think it's Plotly. Yeah, Plotly. That's another kind of like a library you can use, commonly use it to do a 3D or even like 4D or different kind of dimensions of a group over there, of group of data over there. But I think he used more advanced like a software, definitely more than this. But the basic ones, if you want to start this kind of program yourself, is those two.
Yeah, I agree. Plotly is a very nice interactive visualization tool. It's like way better than the conventional ones like Matplotlib or Seaborn.
Yeah. So
our
basically,
last-
you can
yeah.
do everything with that. Basically, it's not only constrained to word. You can also do the products. I mean, imagine just replace each single word with the products. Apple related to orange, orange related to banana, so on and so forth. Yeah.
And the last question is actually about the section you're gonna teach later. I think it's from
Kernel.
Anidia Mitra. Yeah, she asked or he asked what exactly is a kernel. A kernel.
All right.
Sorry.
Yeah, let's answer your question right here. Let's go through this section right here. So kernel. So one of the powerful strengths of SVM is that it can handle nonlinear. So the point is nonlinear separable data points. Okay. So for nonlinear separable data points, SVM can do way better than a lot of like traditional algorithms like a decision tree, random forest, and so on and so forth. Okay. So consider the following example. Let's start from this. Suppose we have, again, a binary classification problem, 2 groups, yellow and red. Can we still use the linear support vector machine, linear SVM to do this, to do classification? Can we just draw a hyperplane to separate those? Unfortunately, no, right? There's no way you can do that because no matter how you draw that, you cannot separate totally, perfectly separate the 2 groups. So that doesn't mean the problem is not solvable. Actually, this is where the kernel trick steps in. So it's clear that no linear discrimination will ever be able to separate this data. But we can think about, we might project, those kind of like a 2-dimension data sets into a higher dimension, so that a linear separator or linear hyperplane can separate those. How do we do that? We can do this, right? What if we just project these from 2-dimension into 3-dimension right here? Then one is on the top, one is the bottom, right? So it's like, I just make it like a 3-dimension. I put the red on the top and put the yellow at the bottom. Now, can we use a linear hyperplane to separate those? I think the answer is quite obvious. We can't, right? So we can just do a linear hyperplane in the middle to separate those, right? Okay, so I think we have one question. The word hyperplane. How do I explain this? So a hyperplane is more than a line. It's like so what should I say here? Suppose I have two items right here. For example, I have a cell phone right here. I have a cell phone right here. I also have on my AirPod Pro right here. Okay, so one is on the top, one is the bottom. I try to separate those. So how do I do that? I will just draw a line, like hyperplane like that to separate those, right? So one is on the top, one's at bottom. So it's more than a line, it's an extension of the line. Okay, I hope that I can answer that kind of question right here. It's actually more than 1 dimension. Hyperplane usually is like for multi-dimension space over there. Okay, so that's a kernel trick. So basically, the kernel trick means we can actually use different kind of kernel function to transform the data to make it into a multi kind of dimension, and then we can just find the linear hyperplane to separate those. Okay, so this kind of like kernel trick is actually known as kernel transformation. Okay, so there are basically many different kind of kernel transformations over there, which we are going to introduce a little bit later. But the most commonly used one is called RBF. It's called RBF. Okay, so the potential problem is with this kind of strategy is that projecting endpoints to n dimensions over there. So if you have two kind of like, suppose you have 2 kind of groups, we can project into 3 dimensions right here to separate those. What if you have 3 different kind of groups over there, right? You're probably going to do another dimension to separate those. So the more kind of group you have, the more kind of dimension you're going to have. So it might become computationally very intensive as n grows very large. Okay, it might have a lot of different dimensions, just like the word networks I just showed you at the beginning of the lecture over there. However, because this kind of like kernel tricks over here, So this kind of kernel tree is actually naturally built or defaultly built into SVM model. So you don't have to, try to think about how I can just reduce the computational cost over there. It will automatically do the kernel tree for you as long as you specify which kernel function you want to use here. Okay. So for example, for this one here, I use SVM model and kernel is IBF. And after that, I just plot the kernel function. It just gives me a hyperplane. See the hyperplane here. This is the center of the hyperplane. This is the inner boundary. That's the outer boundary. So this can perfectly separate the two groups over there. Okay. So next part is empirical coding. So we talked about the theory of the SVM model. Now let's actually do some, kind of fun experiment using this to do some kind of classification. So let's take a look at the facial recognition problem. So we'll just use the labeled face in the wild data set, which is like a data set embedded in the sklearn library over here. So that data set has several thousands of collated photos of various public figures over there. So our goal is try to assign each kind of picture into the right public figure. Each data point has a picture labeled with a name. So a batch of the data set has been built into the data set is built into sklearn. So I just actually extracted partially of the data set right here. So basically what I do is from sklearn data set, import fetch LFW people, then the data set will be loaded right here. So next part is actually I'm gonna try to think about how many pictures I want to have for each public figure for this data set. I want to have 80, the more the better. So I just want to have 80 kind of picture for each kind of public figure. Then I just use a variable faces to call that kind of data set. So faces will be the data set that has 80 pictures for each public figure. And that's print the faces name, that's print public figure's name. So it has Colin Powell, Donald, George Bush, Tony Blair, so on and so forth, all public figures right here, like famous public figures. And the dimension of the data set is 3 dimension, right? Width, length, height, right? So because it's a picture, so it has 3 dimension right here. Okay. So let's see what kind of public figures we are looking at. So as you can see here, we printed a name, George Bush, Tony Blair, Donald, Colin. So those are all the public figures, or part of the public figures we are dealing with right here. Okay. So what we do here is we have the label for each picture. And now we're going to do a classification and see whether we can, assign that picture to George Bush, assign that picture to Tony Blair. Okay. So what we need here first is a model. So we need a supported vector machine model over here. So for classification, it's called the support vector classification SVC here. So you can just import that from sklearn.svm. So SVM is a bunch of supported vector machine models, consists of supported vector regression, supported vector classification. So if it's classification, it's called SVC. Okay. So next part is the model selection part. So basically, when we do the classification, we try to split the data set into a training set and test set. We use the training set to train the model, and we use a test set to evaluate the model. Okay, so that's why we have train test split right here. And we also have stratified k-fold. So interpret this as a way to split the train test data set automatically. So it can just, kind of like randomly split the data set into training set and the test set many times, and into probably 4 training set and 1 test set, or 3 training set, 2 test sets, so on and so forth. So how do we actually divide different kind of data set? It's a parameter you can set up in this kind of function right here. And this one is more like a straightforward train test split function, where you can just tell them, I want to split the data set in this way. So randomized search CV, basically this is a function we use for the hyperparameter search, which is used for this step, model optimization, which is the second last step right here. Okay, we'll have more details on this later when we talk about the classification. Okay. So what's next? So we also need PCA, which is one of the libraries, one of the functions where or the models we use to do the dimensionality reduction, because we have so many pictures and we have so many dimensions right here, and we want to reduce that. More details, please just go to Chris' part 2 lecture. I will actually explain this a little bit more on with details over there. So I also import a pipeline kind of function, which can make all the stuff into pipeline, starting from the data processing into the dimensionality reduction into the model. Everything can be nested into a pipeline, so I don't have to separate every single component over there. And the last part would be a log uniform distribution, which I use for the hyperparameter search. Okay, so each image contains 62 times 47, or nearly 3,000 pixels. Okay, we could proceed by simply using each pixel value as a feature, but often it's more kind of like effective to use some sort of preprocessor to extract the meaningful like pixels. For example, if you look at this picture, why just not extract that pixel, the eye, the nose, and the lips? Those pixels right here, that pixels on the corner, does that make any sense, or does that help a lot? Not really, right? Those pixels right here, it's not that important. So what we do is try to use PCA to extract the key pixels or key component of the picture to help us recognize what kind of like a public figure that is. Okay, so we use the PCA to extract 150 fundamental components or pixels to fit into a spot vector classifiers. So what do we do here? First, we start with the PCA. So PCA model here, and we specify I want to extract 150 pixels of each picture over there. Okay, and a random state is just a state you start the model. I just set 24. You can set a different number. So that's the first part. Second part is I'm going to feed this kind of model. I'm going to feed what I learned from PCA into SVC over there. So into the classification model right here. So classification model had different kind of parameters. First of all, I just use a kernel because it has more than 2 dimensions over there, right? So you better use a kernel to separate some project into a higher hyperplane or dimensions over there. So I use RBF, and class weight is balanced because this data set each have 3,000 pixels. There's no kind of like like oversampled pixels or undersampled pixels over there. Okay, so next part, I'm gonna make the 2 into a pipeline. Why do I make that into a pipeline? Because if you don't make that into a pipeline, basically you have to change the parameters, those 2 parameters, those 2 kind of function every single time. Or you have to, if you want to make changes, you can make the changes on both of them every single time. And if you want to train the model, you have to train them, separately. If I just make a pipeline, I can train both models just one time. I don't have to train them twice. Okay, so I make them into a pipeline, use make pipeline and PCA and SVC. Basically, that's a new model which consists of PCA first and SVC second. Then the next part is I'm actually gonna specify the parameters to run, or the parameters I wanna search for each model, specifically for the SVC model. For example, the C, which is this C here. Okay, because if we have a large C, that means it's the hard margin. If we have a small C, that's a soft margin. But what's the best C? We don't know. So what we do here is we can do a randomized search, and then the model tells us, what's the best C here. And another kind of like parameters is actually gamma. Okay, so C controls for the margin hardness. It's a regularization parameter. The strength of this regularization is inversely proportional to C. So as you can see here, large C basically means the model has a higher variance. Basically means the model can be generally applied with different kind of data set, but it has a lower bias right here. So the model can be very precise, but it cannot be generalized to any different kind of data set. Basically, it can only use it for this data set. But for smaller C, it has a higher bias, but lower variance. So that model is not precise enough, but it can be generalized to different kind of data set over there. Okay, So there's a trade-off between large C and small c here. So that's why we want to search for that. And another one is called gamma. Okay, gamma controls for the size of radial basis function kernel. If we just use like a RBF function as a default function here. So the kernel coefficient gamma here basically tells you how well this line gonna fit into each point. Are we gonna draw a really rounded like a circle right here, or are we gonna draw this? So a smaller gamma means we can draw this. Just like that. Okay. Compared with this kind of like, you know, first kind of round circle, this circle is more precise. But the problem is that might be overfitting. So you're actually too detailed to each kind of point over here. If we change the data set into a different kind of data set, you know, those kind of points fitting might actually stop the data, stop the model from making a more precise kind of prediction over there. Okay. So that's the two kind of parameters we can train here. You can also train the kernel tricks parameters. It can be linear, polynomial, RBF, sigmoid, or pre-computed. Okay, so those are just different kind of like kernel functions you can use, but each of them have this pro and cons. So if none is given, RBF will be used as default right here. So after that, we specify the parameters, specify the model. So what's the next? That is, I'm going to split the data. Okay, I'm going to split the data into training sets and data and the test sets. So I use stratified k-fold function. I split the data set into five different kind of groups over there. Okay, 5 different kind of groups, k or 5 folds. And I shuffle the data set every time when I actually, you know, divide the data set into 5 different kind of groups over there. So that is, I actually separate data for the training and test set over there. Okay, for the scores, which is actually used for the model evaluation, that could be many of them. So what I use is just F1 macro, F1 weighted, F1 micro over here. So those are just 3 different kind of F1 scores we can use, but you can also use the accuracy or different kind of scores over there. Okay, so this part is try to split the training set and test set for the entire data set. Okay, and that part, this k-fold is try to separate the training set into more detailed training set and test set. Okay, so those are 2 different kind of functions right here. So this one here separates the training set and data set using train test split. So the X or the features we use is the faces data. The Y or the target is called faces target. Random state is 24, test size is 30%. Basically, I'm telling the system that I want 30% of the data set as a test set, and the left data set are all training kind of set. So X train X test, Y train Y test will equal to that. Okay. So what do we do here? And last step would be search for the hyperparameters for the pipeline we just made. So we use a randomized search CV here. And for the base parameter, we just tell the system, I want to search a parameter for this one, for the pipeline I just made. Okay, so that's the first kind of argument I put over here. Second one, I want to tell the system what kind of parameters I want to search. Those are the parameters I want to search, C and gamma. Next part, scoring. What kind of evaluation should we use for, you know, those can search? I need a standard tell me, oh, is this C good? Is this C bad? You know, why do I actually care about, you know, this C more than that C? So that is why we have to use a score. We have to use a standard to evaluate different kind of parameters over here. So I use the scores I just defined previously. Refit means you are going to use this kind of score to refit the data set you use for the training at the end, because you cannot just, you know, use all of the standards right here. You have to find the specific one at the end. Okay, so I'm going to use that one as an ultimate kind of like a, you know, standard over here. CV, I'm just going to do k-folds. I'm going to just use that kind of separation I just defined right here to split the training set and data set, training set and test set. A random test is 24 here. Okay, So after everything, I'm gonna fit my train set and kind of like X train and Y train into the search, randomize the search kind of like a model over here, and it takes me 34 seconds. And the best parameter for the SVM model, it tells me is for gamma is 0.5 and for C is 11.505 right here. Okay, so the best score is only 30%. It's only 30%. It's not high at all. Okay, so let's just look at how the model performs in terms of the picture prediction right here. Okay, so for this one, I just plot all the pictures right here. All the pictures I have, just like the same one as we have right here. And for those ones, the red kind of word basically tells us that one is not a right prediction. So black words basically tells me that's a right prediction. So basically, as you can see, oh, for that one it's George Bush. For that one, George Bush. For most of the figures that isn't or aren't well predicted are George Bush right here. Okay, so that's why the score is only 30%. Because if you look at the original kind of picture data set, most of the faces right here are George Bush. Okay, that basically means George Bush has more data points than any other public figures in the data set. So we need to probably undersample that a little bit because there's an imbalance between the different kind of public figures into a data set. So when you feed the data set into the model learns more on George Bush instead of other rarely appeared public figures over there. Okay. So yeah, so basically that's how we can do this classification right here using the SVM model. So I'm gonna answer some kind of questions really quickly before I end my part right here.
We actually have a lot of questions about this part.
Yeah.
Okay, so one question is from Carolina. She asks, could you elaborate how both k-fold and train test split work together?
So train test split basically means you're telling the model, I want 30% of the test, want 70% of the training. It will just separate in that way, not randomly. It will separate in the certain kind of way. Okay, but for the k-fold, it's randomly splitting the data set. You just tell them how many groups you want. For example, 5 groups. It will just separate the data into 5 groups, but randomly every single time. So each time it doesn't have the same kind of separation over there. Okay, each time it doesn't have the same kind of separation. Suppose except you actually fix the random state over there. And both of them can be used for training and test the data split over there. But depends on which one you want. Most of the time, I just use a K stratified, kind of like a fold over there for the like training test set split here. But here I show you both to give you 2 choices that you can make by yourself over there. Another kind of like important stuff is that the stratified k-fold is a function or is a way to separate data. It doesn't give you the data. It doesn't give you X train X test, Y train Y test. So basically, you can feed that function into a randomized search function as a way to tell them, oh, I want to separate data in this way, but it's not going to give you X train X test just like a train test split. Okay, that's another difference over there. So when we use pipeline, are we essentially filtering out the non-relevant characteristic and merge it back to one dimension? Not really. That's what I mentioned, right? That's what I mean right here previously. So we didn't do any data pre-processing before PCA here, right? For example, just like I mentioned, we have a lot of George Bush right here, but we didn't actually undersample that compared with other kind of like public figures. So that's why when we do the classifications, the model will tend to learn more from George Bush than any public figures, other public figures over there. So, I mean, if you want, you can do a little bit of filter, or we call that undersample or oversample of other kind of public figures, or undersample of this, popular public figures to make the data more balanced over there. But we didn't do that right here. Any of these parameters are hyperparameters. Hyperparameters are the parameters you can tune, or the parameters you care that you want to tune to make the model into the best version. all those kind of parameters, all those, add these are all parameters. But which one are the hyperparameters? That is the tunable parameters. If the parameter has a certain value, it's not a parameter. It has a fixed value, it's not a parameter. If a parameter is tunable, usually we call that hyperparameters. Okay. So all of these are hyperparameters for sure, but you don't have to train all of them. It depends on your needs over there. Random state has infinite choices, right? It's just the initial state you started when you actually use a model. So you tell the model fix the starting point. You can start from here every single time. So usually we don't call that hyper. How do we fine tune model besides change the sample data as accuracy very low? Just like I mentioned over here, basically you can't just tune the model without changing the data to make the model best version. Because the problem for our question here, for our kind of task here, is that the problem happens with the data. It doesn't happen with the model. The model probably is okay, but it's actually the data set here doesn't work that well. Or if you think that the model is not working very well, you can change to another data set, or sorry, to another different kind of like a model here, do the same kind of classification, see whether it gives you higher parameters over there or higher best scores over there. But generally speaking, when we actually find some problems with a lower score, we started from the beginning. We search for the errors in the data and we check each step by step until we find the problems. Then we actually, then restart the whole kind of loop and try to actually find out which step has a problem, and we fix the problem, then redo the training over here. And for this one, obviously, the problem is the data here. This is called, how do you evaluate the data set? Good question. So there's no general way to evaluate data set. For example, for this one, if you have the imbalance problem, like imbalance problem right here, you can do EDA. How do we do EDA? For each public figure, list the number of the pictures they have and see whether they have the equal number of the pictures. Okay, so that could be one way, right? Or you can just do a group. For American, public figures, how many pictures over there? For UK public figures, how many, figures over there? So basically, you have to do a bunch of descriptive analysis or statistics yourself to find out whether it's balanced or imbalanced over there. So there's no general function or just like a model I showed here to do that. Oh, I think I answered. I will just type right here. So there are two basic kind of functions or library you can use, which is one is called word2vec. Another one is plot. Word2vec is natural language, like a natural language neural network model we use it to actually construct the different kind of connections between, or the lines between different kind of words up there. Plot is a one you can use to actually, make that into a graph like that.
I think that's it. That's all of our questions right now.
All right, so there's a little bit of conclusion of the pro and cons for this kind of model right here. If you're interested, you can look into that as well at the end. If you don't have any other questions, I'll just, just give you guys a break and you guys can, come back and, keep going from part 2 of today's lecture.
Sure, then we'll have a 10 minutes break. And during the break, I'll send out the attendance sheet to our Zoom chat and our Slack channel. So please check it out and let us know if there's any issue. For those whose Zoom name doesn't match their registration name. So please check it out. See you in 10 minutes. So it'll be,
all right.
Yeah.
All right, thank you so much. If you have any question, please feel free to actually, reach out to me in the Slack channel. I will try to answer all the questions over there. Okay. All right, see you guys.
Okay, now it's 2:21 p.m. Let's start the second half of our class of today. The second half will be taught by Chris. Let's welcome Chris.
Yeah, sure. Thanks, Jane, for the introduction. And yeah, thanks to Danielle who gave us a very very good walkthrough about the general ideas of machine learning and with a focus on supervised learning. And what I'm going to talk about today is another topics in machine learning, which is unsupervised learning. So what is unsupervised learning? So let's use Daniel as an example, right? So Daniel is such a good tutor, and he gave us some good examples about the theories and the intuitions and application cases for machine learning, and therefore we can learn from his prior knowledge in machine learning and so to form our own knowledge about machine learning. But on the contrary, so what I'm going to do is to so instead of using my prior knowledge, I probably threw out some questions, which is not from any of the knowledge, and it's rather. So I would like to, for you guys to be more interactive with to have more interactions with me, so we can look into those machine learning problems in a different angle. So without further ado, so let's get started. So the first topic is I'm going to cover is called PCA. It's actually an algorithm on the what is called that? So dimensionality reduction algorithm. So, and it's a PCA stands for principal component analysis. It is probably the most used and most historical algorithm in this area, and everyone wants to learn a little bit to get started with dimensionality reduction. We'll probably get started with the PCA. So why we wanted to do PCA? There are two major reasons. First of all, it helps us visualize the data for higher dimension problems. Why is that important? So remember when Daniel explained the hyperplane and using the SVM as an example, and there's a question from the audience, and what is a hyperplane, right? So and basically, so hyperplane is a quite an abstract concept, right? And but so as a human being, so we are so used of the 3D spatial space, and so our imagination unlimited. So we can, and anything less than 3D, like a 2D or 3D, and we can have a good and so understanding and intuition about that. But anything is, and when so we are dealing with higher dimensions, so things could get tricky. And here's a quote from the one of the most famous machine learning giants in the world, the Professor Geoffrey Hinton. He said, to deal with hyperplanes in a 14-dimensional space, visualize a 3D space and just say 14 very loudly. Everyone does that. And yeah. So I did it quite often. So whenever I need to deal with high dimension space, so I just plot it in 2D or 3D space to help me better understand it and better visualize it. And that's the first purpose of PCA, or dimensionality reduction, to reduce the dimensions so we can visualize in a 2D or 3D space to have a better picture. The next purpose for the next purpose of PCA is to reduce the multi-collinearity. So what does that mean? Multi-collinearity or collinearity, or just to simplify it as a collinearity. So that's a little bit tricky concept, but instead of diving into too much mathematical details, I'd rather to give you some intuitions about an algorithm. Let's get started with a very simple question. So actually, this is a question for every one of you. So suppose you were to develop an algorithm to make predictions on the housing and the house price, and what feature or what variables are you going to use? The hint is so we can probably use something like the square, the size of the house, and number of bathrooms, so on and so forth. But what else? What else you can think of as a features to model the problem? Neighborhood. I saw the answer from the Carolina neighborhood. Anything else? Unemployment. Yeah, that's a very good one. So I would say it as I would expand it as so some demographic statistics for the neighborhood, right? So, and if we take a look at a neighborhood, so you probably want to use something like some average income, household income, populations, and so male female ratios, so how many, and kids ratios, and education levels, right? So those kind of features as for the to use them to build to develop your model, right? So number of bedrooms, and yeah, so if it's near to famous schools and locations and so forth, right? So, and you can, and you guys are absolutely right about the features that can be leveraged for this problem. But the challenge is, so as we, and the possibility is infinite. We can add as much as many features to help us build up the model. But the challenge is, so as we add more and more features, so we are introducing more dimensions to the problem. And therefore, it becomes hard for human to interpret a model. And even the model itself, some of the machine learning models, they will have some hard times with the high dimensionalities, right? So, and if we threw not even tens, or not even tens, but so hundreds or even thousands of features into the model, so model can easily get confused. So how can I do with that many features, right? So, and therefore we need to find out a way to help us. What are the most important feature, not features, but features, and that can be used for modeling problem. And sometimes you can be easily confused by the two approaches. So one is the naming the feature selection versus a feature reduction of dimensionality reduction. And sometimes people can get confused by the two concepts. So let me use an example to explain the difference between those two. So let's take a look at this chart. Okay, and regardless of the value, let's rewrite the value. So it's probably 1, 2, 3, 4, and blah 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 blah, and all the way to, let's say, 15. And we see the x. Let the x-axis be the bedrooms. And what about y? So we'll probably do the same thing, just to get rid of the scale. And 0, 1, 2, 3, 4, blah blah blah, and 10 or 12. So let the y-axis be the number of bathrooms. bathrooms. So my question to every one of you is, so if you have to pick one feature to model the house price, which one would you choose? Bedrooms or bathrooms? So they seem to be, so correlated, right? So based on the distribution showing here. So, but the question is, so if you have to use just one, which one would you choose and why? Bedrooms. So there's as bedrooms, and intuitively, I think you guys had the right answer. So bedrooms is probably a little bit better features to model the problem. But why? Why bedrooms, not bathrooms? So people has a very good intuition on the so human beings has a good intuition on this kind of problems, but there's some so the profound theories behind this thing. So intuitively, so what we very naively, so we can probably use the dispersion, so like the dispersion to matter as one way to help us decide which one to choose. So if we take a look at the bedroom, so it may have a wide span, as compared to the bathroom, as compared to bathrooms. And if we have just plot the distribution, right, and we'll see the bedrooms may have a, sorry for the drawing. If we draw the distribution, right, so we may end up finding that the bedrooms may have a higher standard deviation or variance as compared to bathrooms, which makes it so a little bit a better choice. But why? So the wider or the bigger variation or standard deviation is a good thing from the modeling perspective. So the reason is quite simple. So if we draw a line here, right, so we would see, so there are some duplicates. But if we draw a line vertically, so we would say, okay, there are some duplications. But if we draw another line horizontally, right, so we would end up with more duplication, even more duplications for so bathrooms, which means so so the bathrooms mean so when we were to use the bathroom only, we would lose more information as compared to bedrooms because of the more duplications, right? So that's a very so the very simple theory behind the thing, and everyone can easily understand why so bedrooms is a better choice for bathrooms. So, and if we were to apply some algorithm to help us find which features is more important than another one. So, and using the result to get rid of some other features to make this model simpler. So this technique is called feature selection. And using feature selection, we would end up with less features to be used for modeling the problem. So this is for called feature selection. And on the other hand, so what is a dimensionality reduction? So let me erase it. It's even more intuitive. So can you think of a way to better model it instead of so discarding instead of so getting rid of any of the feature? I mean the bedrooms or bathrooms. So let me make it a little bit, clarify the question a little bit. So instead of discarding any of the feature, which are bedrooms and bathrooms, can we come up with a better way and to allow us to use a new feature? To allow us to use a new feature instead and to model the problem. instead of instead of 2, but without having to discard or discard any of the feature. So this problem is probably a little bit more challenging question, but intuitively, I think there some of you may have realized. Okay, so if we join line here, and just make projections of every single point and to this line, and using the value from the value to as our new feature to model the problem. So this is probably a better solution. Why this is better? So because by make projections of each point to this line of this vector, so we end up with way less duplications for every single values on this line, right? So I'll just pause a little bit to let you guys think about why make draw a vector along this direction and create and convert each point, and you create the projections of each point on this vector is a better idea. So anyway, this is the fundamental ideas of finding the principal component, and you know what? This vector is just one of our principal component. Is our principal component, and another principal component is probably this one, which is the diagonal to the first principal component, and we call it this one is the first principal component, and this is second principal component. And why this could be of help? So I actually find a very good article online. So showing up here. Okay, let me clean up my drawings. It has a very nice visualization, and using some data points are very similar to the chart, chart we just saw. And so each of the points are the raw data, right? And we're just making the dots, red dots are just projects on vector, and the red lines are the distance from each point to the vector. So if you stare at this visualization for a few seconds, and you'll probably find that when we were to use this vector, we end up with the minimal summary of the distance from the point to the vector. So in other words, so we can use this vector as the principal component to represent both bedroom and bathroom with minimal loss of information. So that's the fundamental idea of the principal component. Yes. Okay, someone has already found that. Yeah, thanks, Carolina. And this is exactly, just 1 second, let me see if this is. Sorry, 1 second. Yeah, this is exactly the link. And yeah, so that's the intuition of a principal component. But another way to think about that is this one. Is a visualization again. So you can think, each of the red lines as a string, and so in order to find the balance, right? And in order to find the balance, so the string will pull the longer the string is, and the force applied on the force applied on the so the axis will become larger, and therefore so in order to get a balance, so it would end up with vectors like this, right? And as you can imagine, so another way to have a balance is this one. And these two are the principal components. And what are the names of those two vectors? We have in statistics, we have some special terms for those two vectors. They are called eigenvector. They're called eigenvectors. So essentially, it converts the problems of of finding the most representative components to the question that how can we find the eigenvectors for metrics, and what kind of a matrix. So and there are definitely some method behind the scene, but there's I just don't want to further confuse you, but the whole idea is so when we were to work with multiple features, we can so first of all calculate the covariance matrix using those features and the examples, and then calculate the eigen and find out the eigen values and the eigenvectors, and then we can use based on the eigenvalues and the rank, just based on the rank of the eigenvalues, to find out the most useful eigenvectors, which will be the the principal components to represent the all the features. So that's the whole idea. That's the whole idea of principal component analysis, PCA. So again, so I'm going to go back to the notebook, and I'll pause here and probably answer some of the questions here. Okay, so first of all, Lisa had a question. Possible to zoom this in? The text is pretty small, even on my fairly large screen. So which specific web page you mentioned? Yeah, if you can let me know which web page you are specifically interested in seeing, so I can definitely zoom in. And the question from Sunil. How do we arrive at the point of a rotation of this plane? And it's quite simple. So, sorry. Trying to, again, so let's draw a line, right? And for every single point, so we end up with, if we make projections to the vector, and if we just add up the length of every single line, and calculate the minimum, and just trying to find the the minimal summary of the distance of those, the minimal summary of those lines. So, and we can find we can find the vector. We can find the vector. That's just one way of doing that. But so more formally. So we would just, so use this formula. First of all, calculate the covariance of the so the features and the examples, and then calculate the eigenvector and the eigen values, and this can be done easily using some packages like NumPy, and but in practice, we don't typically write up everything in so in the detailed steps, but rather so we will probably using some so existing packages such as cyclones decomposition package to help us do that job. So we don't have to do it from scratch. Just a second, let me find out the chat. Oh, where's my chat? Sorry, I think I lost my chat. Okay, yeah, there we go. Can you, another question was from Winsor. Chris, can you tie the eigenvectors back to the house pricing model? Okay, so if let's take a look at this one. Let me write up something. Okay, first of all, let me close this window. Okay, so keep in mind that, so we end up with bathrooms. This is bathrooms. And this is bathrooms. We talked about feature selection, which is, so among those that many features. So how can we find the most important one? And we agree that a bathroom seems to be the more important one feature as compared to bathrooms. But when we were to apply PCA on top of bathrooms and the bathrooms, we probably end up with two vectors, this one and that one. We can use both, or you can use just one of them. So let's say we just use we decide to just use so one principal component, and then we decide to use this one, and this is a straight line, right? And then we just so convert it into another base, right? So we sort of rotate it, and every single line, right? So for every single line, so for instance, so we have one line with a value of 3 bedrooms and 2 bathrooms. And if we say this line is, so the line is y is equal to 1 plus x. X is bedroom is equal to 1 plus bathroom multiplied by 1.5. I'm just making the numbers, right? And then we can project we can so convert each point and project it to make projections on this line. And we can then calculate the distance from this line. Let me do it a little bit better. So this is a line, right? So, and we decide to use this as a principal component. And then we can make a straight line diagonal to the vector, the principal vector. And then we can calculate the value of the length between this point to that point, and then we end up with new value, and the new value we just call it v, right? So, and this is 1 point, and then another point. So we just calculate it we call it B2. And instead of using two features, we are left with one value or one feature, which is represented as the value of the distance from the projection of every single point to the y-axis. And so this helps us to convert two features into one. And in other words, so we reduce the dimensionality without having to lose a lot of information. Does it make sense? Okay, I'll go back to the Lisa's question, your screen share. So I think it's probably because of the resolution. Okay, does that look better? Yeah, cool. And another question from Sunil. So wanted the eigenvalues become the second dimension? No, we actually, so if we apply if we were to find the eigen vectors, we probably find that there are two eigenvectors. One is this, another is that, right? And there are two eigenvectors, and but based on the and what are the role of eigenvalues here? The eigenvalues, the magnitude of eigenvalues are used to help us identify which principal component is more important, right? So and most likely, so if we were to calculate the eigenvalues and the eigenvectors, we probably find that the eigenvalue for this one is greater than that one, and which means that vector is more important than, I just use the different color. And yeah. So if we were to calculate the eigenvalues, we probably end up with finding, so the eigenvalue for the blue vector is larger than the eigenvalue of the, so the red vector, and we'll probably, and therefore we'll see, okay, the blue principal component is more important than than the red ones, because so it takes account of the most of the variance of the two variables we are talking about. So yeah, does that answer your question? Again, so I think I lost. Yeah, cool. Yeah, so this is a quite interesting topic, and I found that there are a few resources online that are particularly, intuitive and straightforward. This is being the one, and then another one is a video clip created by author called 3 Blue, 1 Brown. That so author is fantastic. They have he had lots of great videos online. So I would encourage you to check it out for some for more food for thought. And I'll be sending the link again to everyone. So you can, yeah, I love it. Yeah, so I love 3 Blue, 1 Brown too. Okay, so go back to our topic. Rest are pretty much very simple. So so in order to let's just use let me just use an example to demonstrate so how PCA helps the modeling as well as the visualization. First of all, we'll take a look at how PCA helps reduce the dimensionalities, and therefore so reduce the multi-collinearities, and therefore help the model to get a better performance. So for this one, for this case, we'll be using a very widely used data set called Irish. Basically, it comes with 4 features. So let me run it. Okay. And oops, I think I probably need to start from the beginning. Okay. Let me run it again. Maybe I have run it several times, so. Okay, I don't know what happened here, but I do have a no-code version. Okay, I have a tuple in my code. I think this. Okay, I have a no-code version. Yeah, thanks for reminding me. But let's take a look at the no-code version. Run it, and we know that the feature, this set, which is called Irish. So you can see, as you can see, so data has 4 features, and we can take a look at the feature names. And there are support length and the support width and the petal length and the petal width, right? So, and given it's a 4 dimension, it comes with 4 features, so we cannot visualize them all. So instead, we just sort of visualizing into 3D dimensions. Okay, next thing is so we can train a model, naive model using decision tree classifier, and we can check we can use a standard train test split and to leave so to use 70% of the data for training and 30% of the data for validation. And then we validated the model's accuracy, train a model using this line. And yeah, so first of all, define the model and train the model and make predictions and compare the predictions against the ground truth. And we end up finding that accuracy is 88%-ish. And the next thing is, let's reduce the dimensionality. Instead of using all of the 4 features, can we reduce the dimensions and make it 2? And therefore, we do the so we can use this one to fit the data, and we end up with a feature called new data set called feature XPCA. So as you can see, it has 2 columns, meaning there are 2 features. And using those 2 features, we can plot the features in the space, in a 2D space, because so we reduce the dimensionality to 2. Therefore, we can visualize them into 2-dimension space, right? So, and clearly the data are separated very nicely using the 2-dimension. Previously, it's hard for us to it was hard for us to visualize the data into a 4D space array. So, since we've reduced the dimensionality to 2, and we can plot it on the X and the Y, which doesn't have any substantial physical meaning, but as you can see, so we have the data pretty much nicely separated. Which means, so yeah, so the dimension, the PCA does find the so most representative information for us. Okay, and so we can then we can train the model using the same trick, using the same steps, and validate the results against the same, so the tested data sets, and we end up with a little bit better accuracy as compared to using the all four original features. So, which means, so yeah, so it did work. So PCA did work, and just one thing. So some of you may have found, there's a statement here, right? There's one line code here, x centered equals to x minus x means. So it's just to facilitate the, so the calculation of the covariance, because of the covariance, if we write it down, it's like x minus mean. Mu is basically the mean of x. Okay, so, and it's just to simplify. So you don't have to do the same thing, because so it's the purpose of this line is just to so simplify the calculation. But this is, again, so this is not necessary. Okay, so a few questions from the audience. Caroline asked, how can we know which are the features we are using for the prediction after PCA? So first of all, after the PCA, after applying the PCA, we end up with features that doesn't seem to have some substantial physical meanings, because they've already, so they are combinations, linear combinations of those features, the original features. Let me show an example. Okay, so we can use this one to demonstrate. And in fact, you can see a very nice breakdown of the two components. Basically, what it tells is that, so there are two components, right? Because we specified the number as 2, and the first combination is a combination of support length and all 4 features, and with different weights, right? And you can see, so yeah, so support length, and so the has more contribution to the attributes to the more to the most to the first component. So therefore, so let's imagine we are working with not just 4, but 100, even thousands of features, such as so the using the demographic data for modeling house price, right? So we may end up with correlated features such as median household income, or mean household income. These two are pretty much correlated, right? So and not to mention some other features like individual average individual income, or so the incomes of people whose age is about 40 and things like that, right? So these features, so the features for related to household income and generic income, they're pretty much so are correlated, right? So, and if we create so we create some so the if we were to use PCA to reduce the dimensionality, we probably end up with some principal components that are specifically one of the principal one of the components is related to generic income, and another one is related to the location, and another one is related to age, and so on and so forth, right? So, and you can probably using this property again, so the PCA components, so you can we can have a so the interpretation, so we can get to the interpretation of attribution from the original features to that specific component. So there's a question. Yeah, no worries. Okay, so next one is so we can use I'm be using the another famous data set, which is called MNIST. So if you have taken any machine learning courses online or anywhere else, so you probably have been familiar with this data set. Basically, so every example of the data set is 28 by 28 image, and standing for numbers from 0 to 9. Right. So, and today, today our purpose of today is not to to demonstrate how to model it, but rather so we'll be demonstrating how PCA can be used to reduce the dimensionality and therefore visualize them and have modeling it more efficiently or effectively. So basically, we can so the raw features, the raw data sets comes with is again 28 by 28 pictures. So if we expand it, so we end up with 784-ish. Let me see, 784. What is that? So X. Okay, so it just uses it just comes with 4 features. I don't know why this is 4 features. Maybe it's just a small setup for the actual this set. But anyway, so if we were to apply the PCA again and to reduce the dimensions into two, and therefore we can visualize the all the examples in 2D dimensions, and so and if you take a look at this diagram, right? So you're probably okay. There are some groups of points here, and we can reference to the color. Okay, there are zeros, and the zeros are very nicely, so grouped together, and the ones grouped together. And what is that? This is 6, right? And that one is 3, right? So clearly, so after the dimensionality reduction, so we can easily visualize the entire data set in a 2D space. Okay, but there's a better version of in terms of visualization. So another dimensionality reduction algorithm, which is called TSNE. TSNE is another dimensionality reduction algorithm, and it has a little bit better effect in terms of visualizing them. So, and the usage is quite similar, right? So, and we just define the TSNE model and train it and fit it, and we end up with again 2 new features, and using the 2 new features to visualize it. So, and you can see, so the data are even more separated, right? There are some differences between PCA and TSNE, but that's another focus of today's topic. So what I want to mention is that if you want to have a better visualization, particularly on a 2D or 3D dimension, instead of hoping to reduce the multicollinearity, TSNE might be a better choice because typically it comes with a better visualization effect. what is the why are there some clusters that are from far away? That's a very good question. So I guess just let me erase the. I suppose you are mentioning some outliers here, right? Like this one and that one. So first of all, like let's take a look at the which groups it belongs to. So this is for ones, and we can have some guesses on that. So and what is the closest one, and which is blue and 2. Okay, so my hypothesis is that so for those ones images that are far away from most of the ones and more closer to 2s. So it could end up with something like that, right? It's still one, um, 2. It's hard to say, right? So, and things could be even a little bit tricky if it has some, so something like that. Sorry. Far away from what? Each other? I guess so. Yeah. Yeah. So, and using this way, so, and it would be nice. So that's the power, and that's actually the power of a visualization, right? It's not always the visualization doesn't always confirm our assumptions, but sometimes when the visualizations disconfirm our assumptions, that's even more interesting because that's probably most likely they are indicating something that worth deeper diving into it. And in my experience, so whenever I saw something like this, I would dive into it and take a closer look at it immediately. And quite often, so they just give me more insights and more findings and about the problem we are analyzing with. And again, so my guess is I could be wrong. So but I would encourage you guys to do some experiments on this one to confirm if the hypothesis is true, which is, so there are some images which are for images are for ones, for number digit ones, but they are a little bit curly and making it look more like 2s or some other numbers as compared to ones. Does it make sense? Okay, anyway, so another question from Windsor, so which is the PCA only used for visualization, or can we use it for reduce the size of models for lower computing devices, for i.e. mobile devices? Yes, of course. That's the second. So the first, keep in mind that so at the very beginnings, I mentioned that there are two purposes for PCA or any dimensionality reduction algorithm. The first one is to help visualize it into the 2D or 3D space. And the second purpose is to reduce the number of features and therefore reduce the multicollinearities and to help us, to simplify the model and sometimes and can even, improve the model performance. And just a side note that so the Shani mentioned at the beginning of the session that Carson and I we worked together to win silver medal in one of the most recent calc competitions, which is called I couldn't recall mechanisms for
Motion actions.
motion action. Yes, thanks for question. Basically, we are challenged to find out to make predictions on response to when we apply some the doses on specified DNA. So what would be the response? And for DNAs, so typically we would be using so the cells to describe it, and so there are many types of cells, and each cell is represented as a feature in the data set. And one of the key to winning the computation is exactly so the dimension reduction, because many of the features, many of the cells, they are very well correlated, and which could confuse the model, any machine learning model. And using dimension PCA and other dimensionality reduction algorithms actually helped us a lot, to improve the model's performance. So yeah, anyway, just a side note about that. So the last interesting topic for PCA is say we find we reduce we are working on the data set which has 1,000 features, and we applied PCA to reduce the dimensionality from 1,000 to 50 or 100. Let's say 100. But out of the 100, so how many of the principal components can be used, so to take account of the so the entire data set, to represent the entire data set. There's the typically we'll be using the so the a matrix called the explained variance ratio. Basically, it tells how much of the variance of the from the original features can be explained by the accumulated number of accumulated principal components. And we can typically we would use the 90% as the so the cutoff. But you're free to you're free to use so to use any of the cutoff like 95 or 85 to decide which how many components are needed for your model. So here's the very quick few lines of code to help you do that trick. So yeah, so again, so I probably pause here a little bit while and to see if there's any questions for PCA dimensionality reduction, and then we'll be moving to the next topic, which is clustering. Okay, if there's no further question for PCA, so we'll move on. So clustering is another very useful unsupervised algorithm, but sometimes people can, including myself. So at when I get started in learning machine learning, one of the questions I wanted to ask is, what's the difference between clustering versus classification? Because they look quite similar, right? So they're both of them are trying to so the create some groups and put and assign each point to a group. But what's the difference? The most significant difference between clustering versus classification is that, so for classification, we will need some neighbors or neighbored data for us to get started with to train the model. And it's like, so example is being, again, so let's use the MNIST, the digit data set example, right? So, and if we've already had some neighbors for every single pictures in the data set, right? So, and we already know, so what the picture is. So in that case, so we can start training a classification model. But imagine that, so what if we don't have what if we don't have so a nice neighbors for that problem? For instance, so if we were to find out, again, so let's use the house pricing model as an example, right? So, and if we were to answer the question, if we were asked by the business holders with a question like, can you figure out how many types of houses? Generally speaking, how many types? And there's no specific definition on the types of houses. Just think about that. How many types of houses in the market in Calgary? Well, so probably the answer could be something like, okay, so there are some, so the suburban family houses in neighborhoods that are in suburban area, like southeast, southwest in Calgary, and the community are pretty new, and there are many single houses. So they're probably, so the one type of the properties in Calgary. And there could be also, the inner city historic, inner city legacy houses, and which which were built in many a little bit along a while ago, like in 60s or 70s, and so there are a lot of bungalows as compared to so the 2 stories, and yeah, so on and so forth. But that requires some prior knowledge about this domain and so the business. But from the data perspective, can we come up with a way to help us identify also how many groups are there in the data, and what are they, right? That's a frequently asked question. And that's when the clustering algorithm becomes handy. So one of the most used clustering algorithm is called k-means. K stands for the number of clusters or groups in the data set. This is a parameter we need to specify. So in another word, so we first of all need to make a guess, a reasonable guess on how many groups could be there in the data set, and then we can start we can start, and then we can tweak it on the way. But first of all, so we need to define, we need to come up with a number for the k. And once we figure out we specify the number of k, and the algorithm, the k-means algorithm, we start looking at all the examples, and trying to find out, trying to find the centroids, the most reasonable centroid for each of the cluster, based on the Euclidean distances of the based on the Euclidean distances. And how does it do the trick? So let's take a look at the specific detailed steps. So first of all, let's come up with some, the toy data. Come up with toy data set. So we will be using this toy data set for demonstrating the k-means algorithm. So in that case, we can easily find that there are three classes, also 3 clusters. If we were to visually and manually inspect the data, so that's probably what we have to say. But how does the algorithm to find it out, to find out the groups, and therefore the cluster every single points into, and assign them into the corresponding cluster? So It's actually quite simple. It comes with 3 steps. It comes with 3 steps. The first step is we randomly initialize the starting points, 3 points, and the 3 being the number of k. So if we were to say, okay, so if we specify the value for k as 3 in that case, and the first step we will be doing is to randomly pick up 3 points in this space, in the 2D space, and using them as a starting point. And the second step is to calculate the distance between every single dot to the 3 points. And that's and assign each point to the closest one, to the closest point. So that's the second step. And third step is okay, using the so the assigned groups, because after the second steps, we've already assigned every single points in the data set to a corresponding cluster, right? And the third step is to calculate the centroid of each group, and move the move the previous point to the centroid of each cluster. So this may sound a little bit wordy, but if we take a look at the picture here, so I can probably walk you through with a little bit better. So what does that mean? So let's take a look at this diagram firstly. So we randomly initialize 3 points, which are represented as the red dots, right? So, and for each dot, so we've already had 3 randomly initialized dots, and then we calculated the distance for every single point to each dot. And for instance, if we look at this dot, we will be calculating the distance here, and distance here, and distance here. And given that, so the closest one is for this point, for this specific point, the closest point out of the 3 is that one. And therefore, so we assign this point along with that point, that initialized point. And we repeated the process for every single point. So we assigned all the blue dots associated. Let me erase it. We assigned all the blue dots associated to this dot, and we assigned all the purple ones to that dot, and we assigned all the light blue ones to that dot, the third point. So this sounds not bad, but apparently this is not the ideal, right? So and therefore, so next step for us to do is to recalculate so the centroid, to calculate the centroid of each group. And by each group, I mean this one, right? Oh, sorry. No, we haven't gone there. So for this group, we calculate the centroid, and the centroid being here. And for that one, we calculate the centroid being here. Let's use cross instead to represent it. And we probably found the centroid here. Then we updated the 3 points location and move them to the corresponding group's centroid. And therefore we move it here and move it to here. And we move it. And we move it. Right? So, and then we will be doing the similar thing, exactly the same thing to calculate the distance of every single point to the 3 new centroids, and reassign the groups, reassign all the points to the corresponding groups, and repeat the process. So after repeating it for several times, in only 2 or 3 times of repeating it, the process for 2 or 3 times, so we end up with very nice results, right? So, but you got the idea. So by repeating the process for several times, first of all, calculating the distance to all the, so the centroid of the clusters, and then based on the, and recalculated the centroid, and then move the, so the cluster the centroid from the old one to the new one, then calculate the distance again, then calculate the centroid again, and so on and so forth. So, and repeating the process for several times, so, and we end up with very nicely classed results. So yeah, that's the how this algorithms works. But again, so we don't have to manually do that. There are many algorithms out there that can be used for this type of works. And so in that case, we can simply use called scikit-learns. Again, so from scikit-learns dot cluster, there are many algorithms that can be used, and we just need to import. For instance, we just need to import the k-means, and so, and then we can do the thing. A couple of things about k-means. So it does have some limitations. It does have some limitations. For instance, it relies on as you can imagine, it heavily relies on the, so the initializations of the positions of points, right? So, and if we initialize it differently, we probably end up with slightly different results. In order to tackle that, so the one of the ways to get a stable result is to repeat the process for several times, and and then we can average the, do an ensemble on top of that. Another limitation for k-means is that, so it works well with the numerical features, which requires some pre-processing, such as normalization. But so as you can imagine, so what if we have some features like gender, location, postal code, right? So it will be hard, more challenging to use k-means for that kind of features, and in that case, there are other algorithms can be used to deal with categorical features like postal code and gender products and so on and so forth. So, but this is just an FYI. You feel free to check out other algorithms like k-mode and k-prototypes, and which can be used for categorical features. But the k-means, again, the k-means works well with numerical features, but not for categorical features. The next question, an interesting topic for k-means, well, and this is probably the most asked question for k-mean, is how can we choose k? We can. The answer is yes. So we can quantitatively estimate the so the appropriate number for k. So how can we do that? So just imagine what is the best way to measure the performance of k-mean, right? So the answer is seems to be quite straightforward. So if we calculated calculated the summary of the distance between every single points to the assigned clusters centroid, and just calculate it and see if we end up with the minimal number, so we can safely say, okay, we got a good clustering algorithm. But the thing is that, so then you can imagine, so if as we increase the number of k, right, so the distance will always decrease. The total distance is between every single point to the corresponding clusters centroid will decrease as well, right? So, but the effect will become marginal as we add more and more, so the clusters to the algorithm. So a practical way for finding the optimal number of clusters is to use a diagram, the tool called, it comes with different names, but people would just call it the elbow chart, because of the shape of so this one is like an elbow, right? So how can we find the optimal number for k? So we are looking for the so the point where the effect, the distance, the total, the summary of a distance becomes marginal as we add more and more clusters to the algorithm. In that case, so we observed that so when the number of the number of k is 3, right? So and after 3, so if we add more clusters to algorithm, but so the models performs, the improvements of the model performance becomes marginal. So therefore, we can safely say, okay, so probably the best number for k is 3. So this is how we can find the optimal number for k. Okay, all right. So I think that's pretty much what we have of today. So just to remind that, so we given the limitation of the constraints of the time, so we just can't cover so all the aspects of machine learning, including both supervised learning and the unsupervised learning. But hopefully, so we delivered some, so we helped you guys to get some sense of the algorithm, the iterations and the algorithm, and so how practically we can use the so those algorithms for some problems. So yeah, so if there's any questions, I would be happy to address. Is k a hyperparameter in this case? Yes, of course. And this is and when you will apply to the k-means for any problems, so yeah, you probably be asked, yeah, so what is the optimal number for k and why, right? You got, and for that question, so you can use this tool. So the tool we just mentioned, the elbow chart, to help visualize the so the patterns, and therefore you can use this tool to help you visually find out the optimal number for k. So but back to your question, yes, this k is something we need to tune and to specify. Any other questions? How do you interpret the metrics? Which metrics? Like the JCK at the end of, okay. Basically, it's quite simple. So it's just the Euclidean distance between the total Euclidean distance between every single point to the corresponding clusters centroid. Oh, okay. The ARI, AMI, and the whole generated and so on. So to be honest, then, one thing I forgot to mention, and yeah, sorry, I have to, I should have mentioned it at the beginning. So for today's content, so I just used the open source content from a website from this. I think I put from this repository, open source. You can search for ML course. I'll be sending it over to the chat. Just 1 second. Where's the chat? Where's the chat? Chat. Okay. So this is an open source repository for machine learning courses, and we are using it for our machine learning bootcamp as well. And well, so go back to your question. In the original notebook for this course, it comes with some, if I wasn't wrong, so it comes with the contents like the metrics used for clustering and ARI, those kind of things. But to be honest, I find that it's less relevant to the problem because I don't use it, and I don't think many of it's often used by data scientists nowadays. Yeah, so that's why I decided to remove the contents from this notebook. So back to your questions. To be honest, I don't know because I don't use it, and I don't think so they are very intuitive or so very useful for as to be used as a metrics to measure the models of performance. Okay. Okay, so if there's no questions, I think I'll just stop there. But feel free to reach out to me and Danielle through the Slack channel, and yeah, so we'd be happy to address your questions if there's any. Thanks.
Thank you so much, Chris, and also thank you so much, Daniel. I think that concludes our 4 weeks of the Python bootcamp. Yeah, I think I just want to say thank you to all the course leaders that for your amazing joint efforts in making this bootcamp happen. Thanks to Chris, thanks to Daniel, to Peter, to Kagan, and another Daniel, and thanks to Franklin, and a big thanks to Carson, the course leader, for their amazing work in organizing this Python bootcamp. And I also want to express a big thank you to the course coordinators, Jane, Xiaolei, and Monier. So I think without your effort, we cannot make this bootcamp happen. And lastly, want to big congratulations to all of you sticking with us for the past 4 weeks to finish this Python bootcamp. And we all hope that you've learned something useful, and we wish you to continue to practice you and continue to learn your Python skills and apply that to your work. I don't have much to say, just want to wish everybody have a great holiday and Merry Christmas and Happy New Year. One last thing that I want to say is after that, please fill out our survey to let us know what we can do better for our future bootcamps. And Also, please stay tuned for our upcoming boot camps for next year. And for the questions you have in our snack check for about the participants Excel sheet that Jane sent, please keep in mind that we are all volunteers, and we hope that we do our best to accommodate your need. And if there are some questions you have, please address that politely in our Slack channel, and we will fix it. And I think, Carson, are you still there? Do you want to say something?
Sure, yeah.
We're close. Great.
Yeah, totally. So you all hear me okay?
Yep.
Perfect. Well, thank you all for coming, and you all should give yourself a big applause for completing the course. Now it's officially completed. I hope you learned something really useful and had some insight of how Python is used in industry. Remember that this is only the first step, but you are not on your own. Feel free to reach out on the Slack channels, our Bootcamp Slack channel, the Edmonton Pi one, the Calgary Design Develop one. And I'd also like to give a big shout out to our GDG Cloud Edmonton and all of our course coordinators and instructors. Without them, this bootcamp could not happen. At last, I would encourage you to check out our local meetups. So like the Edmonton Pi and PyYYC. Feel free to volunteer or give a talk, because I believe the best way to learn is to teaching and by teaching. And you can also share your knowledge and make networking. At last, I will draw one PyCharm license later and send it out. As usual, the course recording will be available in our PyYYC YouTube channel a few days later. So just give us a few days. And if you haven't subscribed, please don't forget to do so. Again, thank you all for coming, and thank all our coordinators and instructors for the great effort and time commitment. Wish you all the best and good luck in your career, and happy holidays. Cheers.
Super. I think Chris is still sharing your screen.
Oh, yeah.
Just a reminder. Great. So before we say goodbye, do you guys mind to turn on your camera? I think last time in our week 1 we turned on our camera just to see who our classmates. If you are okay, I think we haven't seen all of you during the past 4 weeks. So I'm just gonna I have my I think when you are going to the view, and if you are changed to gallery view, perfect. So view, gallery view, you will see all the participants, and oh great, I see many of you have opened your camera. That's really nice and great to see you guys, not in person but closely in person. I want to once again thank you so much. And also one fact is that I noticed for the about 100 participants in our bootcamp, we have people from 7 or 8 different time zones. So I think we have participants probably not only from Canada, which is great. I'm gonna take another screenshot. I remember I took one on week 1 of the course. So I'm gonna just keep the tradition and take another one by in the end of our bootcamp. So I needed to take, we have 4 pages here, so I need to take 2, 3 screenshot, but I will give a notice, and you can bring on your biggest smile when I see what we should see.
Christmas.
Okay, great.
Okay, cool.
That's great. So I will count 1, 2, 3, and we all see Christmas. And I'm gonna take the screenshot. Okay, I'm gonna get ready for the screenshot. Okay, 1, 2, 3. Christmas.